I really can't tell you how excited I am to be back here after 3 years. I hope you all are as well. I'm going to give you all the latest and greatest about our ongoing, kind of very long at this point, study of the evolution of cold streams in the circumgalactic medium of massive halos at high Z. This is a work done with a lot of folks. Some of you are in the room, Avishai, Frank, Han, and many others as well who are not here. Is this not? This was working before. Oh, that's so sad. Okay. A fun hobby of mine is to count how many times this figure appears in every conference. This is 2 so far by my count, and we're only in day 1. So anyone who cares about galaxy formation has to care about how gas flows into and out of galaxies. Otherwise, you can't really do much. This ties together the 3 large gaseous reservoirs of the universe, the intergalactic medium, the circumgalactic medium, which is in some senses the most complex, and the interstellar medium. Circumgalactic medium is, of course, containing both gas flowing inwards from the intergalactic medium as it interacts with gas flowing out from the interstellar medium, and is both the repository of fresh gaseous inflow as well as gaseous ejecta, which makes it quite complex. Now, you'll notice that even in this cartoon, which was really meant to discuss a very generic CGM structure at redshift 0, they do take the point to show that the gas accreting from the intergalactic medium appears to be flowing in along a filament. And that is indeed the characteristic picture that a lot of us have in mind, because galaxies, galaxies do form within the cosmic web. This is a snapshot from a simulation we ran a couple of years ago using a repo, but what I want you to focus here is these are 2 orthogonal projections of the total gas surface density, and you can see here a cosmic sheet, and if you look at the sheet face on, you can see a lot of very dense cosmic filaments embedded within the sheet. Now, all these little circles represent dark matter halos, so your kind of standard, typical mass dark matter halos typically lie along intergalactic filaments, but the really massive ones, the nodes, the most massive halos in their given environment, lie at the nodes of the cosmic web and are fed by a few individual intergalactic filaments, which are quite narrow compared to the virial radius of the halo itself. And to show that in what it looks like kind of in a single halo, I'm going to show you a movie now from the Vela simulation suite showing the evolution of a pretty massive galaxy from redshift 6 to redshift 4, which you can see is fed by, in this case, 3 cold streams, which feed the galaxy with gas. They also, perhaps somewhat contrary to what Claude André told us, and I should talk to him a bit later, they do feed the galaxy with angular momentum in this case, and they also generate turbulence in the disk, which I know we'll hear more about later this week, and I'm going to let the movie play. Now, it's quite obvious that in order to understand how the streams feed the central galaxy with mass, angular momentum, and stir turbulence, obviously all these 3 depend critically on the state of the streams as they reach the central galaxy. It's going to be very different if you have a very smooth flowing stream or a very clumpy, turbulent, disrupted stream. That's going to affect the evolution of the central galaxy, so that really warrants us understanding the evolution and the structure of these streams. These, by the way, are observations by Chris Martin et al. From a few years ago at this point, showing kind of on very large scales in similar mass halos at similar Z, so 100 kiloparsec scales, you can see what looks to be like a rotation signal of circumgalactic cold gas, which seems to actually resemble this kind of in-spiraling stream kind of pattern that we saw in the movie, suggesting that we may be seeing some observational evidence of things like that. Now, we've heard a lot today about how very massive halos tend to virialize and form a hot halo. Now, hot halos and cold streams don't necessarily live together very friendly. In very massive halos, above 10 to the 12 at redshift 2, we expect the circumgalactic medium to, very mostly be hot at a virial temperature of order 1,000,000 degrees. Now, the classic thinking, and by classic I mean 10 or 12 years ago, used to be that, no, more than that at this point, but used to be that because, I'm getting old, because the streams were so much denser than the standard gas kind of that fills the volume of the halo, the cooling time in these streams was a lot faster than the cooling time in kind of the standard CGM. Therefore, the streams did not shock heat. They remained cold, and they basically free fall toward the center of the halo, even if the volume filling CGM was hot and in quasi-pressure equilibrium. But it's not at all obvious that this works to allow streams to flow all the way down, especially when you get into the central 30, 40, 50% of the virial radius. Streams begin to interact with each other. They can be disrupted by instabilities as they interact with the hot CGM, hydro instabilities, thermal instabilities, gravitational instabilities, shocks, etc. And indeed, a while back, groups started to run cosmological simulations, and depending which cosmological simulation you were to look at, they say streams disrupt well out near the virial radius, or streams make it all the way into the virial radius, into the central galaxy. But you really shouldn't be trusting any of them, including us. You shouldn't be doing should not be using cosmological simulations to answer these questions, because at best, out near the virial radius of a halo, where most of this action is taking place, cosmological simulations resolve these streams by 20 cells, 30 cells, maybe. That's not nearly enough resolution to understand the detailed physics that really governs this interaction. So that's motivation number one. Motivation number two, which I'll just very briefly flash, there are lots of different observations of cold gas in the circumgalactic medium of massive galaxies at high redshift. This is with Subaru, Keck, Muse, KCWI, KCWI, and ALMA. So this is kind of the odd one, out. All these other ones are looking at the Lyman alpha, and the results are quite robust, quite generic. Around pretty much every massive halo at redshifts 3 and above, you see large quantities of cold gas extending out to hundreds of kiloparsecs. And if you believe the photoionization models, a large fraction of the CGM gas does seem to be in pretty dense, pretty cold, 10 to the 4 Kelvin, small, and very metal poor clouds, which seem to indicate some kind of instability happening governing the morphology of these cold streams. And a number of theoretical works going back a while have said that these Lyman alpha blobs, as they used to be called, are indeed observational evidence of cold streams inflowing. I just love this picture because it's a simulation circa 2010, and finally in 2020 they observed exactly the same system, which is a remarkable coincidence. This implies some kind of a dissipation mechanism that allows the inflowing streams to tap into some fraction of the gravitational binding energy of the halo that they gain by flowing from RVR down to about 0.2 RVR. But what that dissipation mechanism was and how it governs the emissivity and the shape of these Lyman alpha blobs as a function of halo mass, as a function of the redshift, was really never clear from any of these early works. And the question is, can we come up with a first principles way, really based on the interaction of cold streams with a hot CGM, to explain this kind of emission and really tie it back into Lyman alpha blobs? So with that in mind, this is our toy model for cold streams flowing through a hot halo. Then you have kind of a spherical hot halo, which is in quasi-equilibrium at the virial temperature. We call that the background. Inflowing cold streams, which have a temperature of about 10 to the 4 Kelvin. That's basically set by the drop in the cooling curve, because these streams are very metal poor. Now, if I assume that the streams in the halo are in pressure equilibrium with each other, I can translate the temperature contrast to a density contrast. And therefore, I learned that, the streams are typically about 100 times denser than the CGM. That's the first dimensionless parameter that's going to govern the problem. Second dimensionless parameter is the Mach number of the flow. Now, here by Mach number, I mean the inflowing velocity of the filament divided by the sound speed of the hot shock-heated CGM. Now, since the streams are flowing in of order the virial velocity, and the sound speed the sound speed of gas at the virial temperature is also of order the virial velocity. Therefore, if I define the Mach number in this way, the Mach number is of order unity. Now, note that that implies the stream is very supersonic with respect to its own sound speed because of the large temperature differential. The third dimensionless number that is going to govern the problem thus far is basically the stream radius divided by the halo virial radius, or you can think of that as the sound crossing time of the stream divided by the virial crossing time of the halo. This can be constrained by the cosmological accretion rate. And showing you this a bit more quantitatively, This is from a paper we had a couple of years ago. The density contrast as a function of halo mass and as a function of the redshift is given by assuming that the halo is at approximately the virial temperature with a correction factor. The stream is at approximately 10 to the 4, and there's approximate pressure equilibrium between the two. That gives you the density contrast as a function of halo mass and as a function of the redshift. If I know the density contrast, and I know the halo density at RVIR, and I know the hot gas mass fraction within RVIR, so this you can kind of extract from cosmological simulations. The hot gas properties are typically pretty well converged. These three together allow you to estimate the actual density in the stream as a function of halo mass and the redshift. This will be important when I start talking about cooling in a few slides. But also, once I know the density in the stream, and again, the velocity in the stream is of order the virial velocity, I know the total accretion rate onto the dark matter halo just from cosmology. And if I have another parameter that says what fraction of this total accretion flows along a single stream, which you can also take to be about a third, because in most cases galaxies tend to be fed by 3 streams, that allows you to compute R stream over RVIR as a function of halo mass. Now, the remarkable thing here is that R stream over RVIR in this model has no explicit dependence on the redshift. It only depends on halo mass. And it seems to approach unity as halos approach 10 to the 11 solar masses, which is when you no longer expect halos to lie at the nodes of the cosmic web, which kind of was an emergent property of this model. It was not put in. Now, to be specific, take a halo of 3 times 10 to the 12 at redshift 2. We're talking about a density contrast of order 200, a stream density of 10 to the minus 2 hydrogen atoms per cubic centimeter, and a stream radius that's about 10% of the virial radius. So these are kind of the numbers to keep in mind. So the first thing you can do, the simplest thing you can do, is take all those parameters and estimate the linear growth rate of Kelvin-Helmholtz instability in the linear regime and compare that to the virial crossing time. And you can see that here is a function of the density contrast, the Mach number, and the stream, R stream divided by RVIR. This is what we did a few years ago now in 2016. Now you'll note that KHI is highly nonlinear. In the region that I expect streams to live, I get a huge number of e-foldings of growth within a virial crossing time, several tens or several hundreds. That implies that linear theory is not directly applicable to the problem. We have to go to nonlinear theory. The second point, which is just too obvious from the figure not to mention, is that you can detect sort of a phase transition here, where the linear growth rate of Kelvin-Helmholtz instability does undergo a phase transition between familiar so-called surface modes, which are the dominant mode of instability at low Mach numbers, and so-called body modes, which are the dominant mode of instability at higher Mach numbers. These are governed by sound waves reverberating back and forth between the two sides of the stream, growing the pressure and the density from the inside out. I won't really talk about this anymore today, but you can come talk to me later if you would like. So we said we can't really use linear theory. You have to go to nonlinear theory. So you can then ask, what is the time scale for complete nonlinear disruption of the stream? How long does it take the stream to fully mix into the CGM? And that's slightly different for surface modes and for body modes, but I don't want to go into the details. The point is that you can, and this is what we did in these 2 papers, you can analytically derive the time scales that it takes the stream to fully mix into the CGM. Intuitively, that scales as the stream crossing time. It's basically shorter for narrower streams. That makes sense. The narrower a stream is, the faster it's going to mix into the CGM. And that allows you to create a plot like this, which is as a function of the density contrast and the Mach number, what is the thickest stream in units here of R stream over RVIR that completely mixes into the CGM in a virial crossing time. And again, okay, depending on where you are exactly here, but the number to keep in mind is a stream where R stream is less than about 5% of RVIR, in principle can completely mix into the CGM in a virial crossing time and thereby shutting off the cold accretion in the cold stream before it reaches the central galaxy. However, everything I've told you about thus far has included only pure hydrodynamics with a bit of cosmology in the background. What happens if I include cooling? Obviously, cooling is important. These are cold streams. So when you talk about cooling, the importance of cooling can be, you basically have to introduce a 4th dimensionless number, which is the ratio of this non-linear mixing time that we, I'm sorry? Oh, sorry. So you have to look at the ratio of this non-linear disruption time, which I'm calling here T shear, to the cooling time. But the cooling time where? The cooling time specifically in the turbulent mixing layer that forms at the boundary between the stream and the background. You have to talk about the cooling time, what I call here T-cool mix. So your fourth dimensionless parameter is T shear divided by T-cool mix. Since T shear scales linearly with the radius of the stream, T-cool mix doesn't care at all about the radius of the stream. You can turn this ratio of the time scales into R stream divided by a critical radius, which you can basically write out like this. Depends on a bunch of different parameters. But you can plot this R stream over R stream using that same model that I showed you a few slides ago. R stream over R stream crit is a function of halo mass and is a function of the redshift. And the upshot is, for most of the parameter space, this R stream over R stream crit is certainly well above 1, and even in most of the parameter space, it's above 10. Implying that cooling is going to dramatically influence the evolution of the Kelvin-Helmholtz instability in these cold streams, and I expect cooling will prevent stream disruption by KHI, as I'll show you right now. So these are simulations without cooling and with cooling, but otherwise the same. The color here is just a passive scalar that traces the mixing of the stream. In the background, the white colors represent pure stream fluid, the black colors represent pure CGM fluid, and everything in between is in between. Without cooling, the stream expands out into the background as you have the Kelvin-Helmholtz instability begin to throw stream material out into the background. That, number one, dilutes the central densities of the stream. Number two, it really pollutes the CGM with a lot of initial material that was initially in the stream, thereby, if you will, diluting the metallicity of the CGM, while the core of the stream remains pretty unmixed and very metal poor. But if I include cooling, and I'm in this fast cooling regime where the cooling time is short compared to the disruption time, I try to fling material out into the CGM, but the material cools really quickly. When it cools really quickly, it loses pressure support and it falls back onto the stream. So you'll note that when this happens, I no longer have so much stream material way out into the CGM. Quite the contrary, a lot of CGM material is cooled in and has mixed inside the stream, thereby enhancing the metallicity of the stream, while keeping the stream actually still dense, still coherent, and still cold. If I run the same simulation, but just renormalize the length scales to put me in the regime of slow cooling, this is what it looks like. It's very qualitatively similar to the no cooling case. This is showing the same simulations, but now looking at the density, just again making the point that without cooling, the density drops. With cooling, the density remains quite high because I condense and entrain more and more material onto the stream itself. Slow cooling looks more similar to the no cooling case. Now, the physical process that I've just described has actually recently been invoked, not to describe cold streams inflowing toward the galaxies, but to describe cold clouds that are outflowing from the galaxies, the so-called cloud crushing problem. This is a paper by Gronke and O, but there have been a lot of other folks, and this list should actually be updated. There are a lot of other papers now discussing this. It's the same basic feature. If you're in the slow cooling regime, a cold cloud flowing through a hot CGM is going to completely disrupt. If you're in the fast cooling regime, the cold mass actually tends to grow as hot gas entrains onto the tail of the cloud. More quantitatively, you can plot the cold mass as a function of time. These 5 lines are in the no cooling or slow cooling regime. All these lines are in the fast cooling regime, and indeed the cold mass seems to grow as a function of time. You can actually look at the entrainment rate, how quickly the CGM gas is being entrained onto the stream. The dashed line here in this normalization is an analytic prediction for the asymptotic entrainment rate, and we can actually do this. The simulations seem to approach at late times the asymptotic prediction, and the cold mass can indeed increase by a factor of a few in the CGM. Come and listen to Han-Ong's talk next Monday, where he will explain to you how we take that entrainment rate and compute the predicted Lyman alpha emissivity from this process, basically finding that you can very easily get of order 10 to the 43 ergs per second in Lyman alpha, which is consistent with most of the Lyman alpha blobs. I won't go into this, but come hear Han-Ong's talk next Monday. In the interest of time, I'll just discuss this super quickly. Another physical process we haven't discussed is self-gravity. Streams can be modeled as self-gravitating isothermal cylinders. When you're talking about a self-gravitating cylinder, the most important other physical parameter is the mass per unit length of the stream, basically the cross-section times the density. And we know from Ostrecker 1964 that hydrostatic equilibrium is only possible if this lambda is less than a critical value, which depends only on the sound speed. And we know from observations of filamentary structures in giant molecular clouds in the interstellar medium that once lambda becomes larger than lambda max, that triggers star formation. So a fifth dimensionless parameter defining the problem is mu, basically the ratio of lambda to lambda max. And as you can see, for a large region of the predicted parameter space, mu is indeed larger than 1, meaning we predict star formation and molecular gas forming in filaments in the CGM. I'm going to skip this in the interest of time, but just to say that there is evidence that this seems to be happening in cosmological simulations. And we ran some idealized simulations. This was also led by Han, and I think he can talk a bit more about runs with gravity and cooling, and with gravity without cooling. You indeed see the formation of these dense bound clumps. But in the interest of time, I want to skip to the final topic, which is what happens when you include magnetic fields. So this is new. This is not new. This is not my result. This is from Burrock and Frommer 2019. When you include magnetic fields, you have to add a sixth dimensionless parameter to the problem. It's the plasma beta parameter. It's basically the ratio of thermal pressure to magnetic pressure. And what these authors found in 2019 without cooling, so with MHD but without cooling, is that MHD suppresses the stream, basically like the mixing of the stream into the CGM, suppresses disruption of the stream and extends the lifetime of the stream. And you can see here a pure hydro simulation with plasma beta of 10 and plasma beta of like 1, and you can see how with the strong magnetic field you really suppress the mixing. If you look at the dense mass as a function of time, this is the pure hydro simulation where the dense mass just drops like a rock, plasma beta of 10, plasma beta of 1. Now, for streams for astrophysical streams in very massive halos at redshift 2, the constraints on plasma beta in the CGM are not very good. The only real reference I could find was this simulation paper by Pockmer et al. 2019. This is the MHD simulations of a Milky Way progenitor, and they basically measure plasma betas between 100 and 1,000 near RVR at redshift 2. So that's pretty high. Is this enough to converge to the hydro result? Number one. And number two, what happens to these results when I include cooling? Remember that cooling extended the lifetime of the stream because the stream and the CGM would mix, and therefore the CGM would cool onto the stream. But if MHD is preventing the mixing from happening in the first place, does everything I told you hold any kind of water? So, all right. I'm going to skip that. Let's just go to the results that we get for MHD plus cooling in streams. So these are and this is work in preparation at the moment. I'm talking about a magnetic field that runs parallel to the stream velocity, but we've been relaxing this assumption lately as well. This is a case with Mach 1 density 100, Mach 2 density contrast 50. I'm showing you the cold mass as a function of time. No cooling are the dashed lines. With cooling are the solid lines. The green line here is the hydro simulation. And these are runs with plasma beta of 10, 100, 1,000, 10 to the 4, 10 to the 5. And you can really see how the amount of cold gas mass growth really drops as I increase the magnetic field strength. And if I look at m dot, you can see m dot for the hydro run, which again approaches this prediction from our previous work, really dropping like a rock as I increase the magnetic field strength. Now, the question from here remains, is this suppression of entrainment mostly due to magnetic pressure suppressing condensation, or is this mostly due to magnetic tension suppressing the turbulence and the mixing? And as the convergence of MHD to hydro, the same with or without cooling. So in the last 1 or 2 minutes, I just want to briefly address this first question without going into the details of the second one. This is showing a slice of the density at pretty late times in a pure hydro run, a plasma beta of 10 and a plasma beta of 1,000. And you can really see how the hydro run is extremely turbulent. Plasma beta of 10 is extremely laminar, and beta of 1,000 is somewhere in between, but probably more laminar than very turbulent. This is a map of plasma beta. And you can see how around the boundary of the stream, where the stream and the CGM interact, even though I started here with a plasma beta of 10, I locally become dominated by magnetic pressure. My plasma beta here is 1 or even slightly less than 1. This is dominated by magnetic pressure. The same is even true in the case where plasma beta equals 1,000, though there the effect is a bit more diluted. And if only really where I go to 10 to the 5, it's hard to see from the picture, but take my word for it, here you are at no point dominated by magnetic pressure. Plasma beta is always well above like 1. Now, what is causing this? This will be the final thing that I'll discuss. These are phase diagrams. So let's focus just on the right-hand on the right-hand panels. Ignore the left-hand panels. This is in the space of thermal pressure and entropy, and this is the mass-weighted distribution of gas in this space. This is a hydro run with no cooling, where everything is at pretty much constant pressure, as coal gas is just mixing into the hot CGM and therefore heating up. This is a hydro run with cooling. The ridge line is still at pretty constant pressure, but you have a large spread in pressure due both to turbulence and cooling. That introduces a pretty large spread in thermal pressure. Now, I've just moved that panel up here, and here I'm showing you the same space, but for plasma beta equals 10. Here the x-axis is thermal pressure. Now you'll note, again, a pretty large spread. You can't really see that ridgeline anymore because the entrainment rate is so suppressed, but change the x-axis from thermal pressure to thermal plus magnetic pressure, and everything is really isobaric now. Okay? There's very little room left for any kind of turbulence, which is inducing the mixing, and everything is really happening at constant total pressure, and that allows us to explain the difference in entrainment rate, certainly most of the difference in entrainment rate. This entrainment rate depends on the cooling time, so naively you compute the cooling time assuming that the density is given by what you would expect for constant thermal pressure, which was true for the cases without magnetic fields. With magnetic fields, you have to compute the cooling time assuming thermal plus magnetic pressure is constant, and then all these curves really lie on top of each other, and this explains most of the effect, except at plasma beta of 10, where there does seem to still be a lot of room for additional suppression by magnetic tension, and we're currently looking into that. And I'll just pull up my summary here. Cooling, self-gravity, and MHD all extend the lifetime of streams, but for different reasons. And what we want to do is eventually combine all of them, cooling plus self-gravity plus MHD plus halo potential plus thermal conduction. You'll have your 7 or 8 dimensionless parameters that will describe the whole problem. It'll be a lot of fun, include a turbulent CGM, and explain the universe. Thank you.
Okay, thank you, Nir. We have time for a quick question, and we can continue the discussion on the coffee break.
Quick question. So I just want to make sure I understand. The cooling comes about because of turbulent mixing layers? Between
Basically.
hot and cold?
Yeah.
Okay.
Yeah.
And so the rate at which that energy is being pumped through that channel, is it basically gravitational potential energy that's being lost, so you're decelerating the flow or not accelerating the flow?
So it's a combination of on small scales locally what's happening is you're dissipating both kinetic energy of the stream as the total mass of inflowing material grows, so it has to share its momentum with more and more mass. Therefore, it slows down, it loses kinetic energy. That's one channel. A second channel is just the hot CGM gas that's being entrained in this mixing layer and cooling is basically dumping all of its thermal energy. And it turns out that in terms of emissivity, because it's cooling in kind of an isobaric cooling flow, most of that emissivity occurs within the mixing layer at temperatures only slightly hotter than the stream, and a lot of it comes out in Lyman alpha. And that's really what ties you into, indeed, the binding energy of the halo, because it has to do with the initial temperature of that hot gas that's cooling, as well as the stream kinetic energy, which is tied to the virial velocity. So it works out that everything is proportional to the halo binding energy, but the local processes are somewhat removed from that.
Okay, so we will leave it here. We thank again Nir for his nice talk. And we meet again in half an hour at 4:30.